Okay, Ben. So we begin. So we're happy to have Ben speaking about gluing constructions for Coulomb branches. Thank you.
All right. Well, thanks for the opportunity to speak. It's always sort of useful. So this is, I probably should have, I think when I originally wrote these slides, the paper wasn't on the archive yet, but this is based on a paper that went on the archive yesterday, joint with Tom Gannon. So it's always useful to give a talk, when you finish the paper where you realize like, oh, I should have put this that way. And so, yeah. All right, so just as basic background, I know many of you know this, but probably there's someone here who doesn't. I apologize to you if you don't. There's a very powerful construction where one can construct a specific kind of quantum field theory, a 3D n equals 4 quantum field theory, by looking at sigma model. So looking at, a three manifold.
Oh, I think everybody has to be muted. Sorry about that. Okay.
But you are the host.
But I'm muted.
You could mute everybody. At any given point, you could mute everybody.
Yeah, you're right. Yes, I'll try to do that. Sorry about that, Ben.
All right. Where one can construct a 3D QFT, not TQFT yet, by looking at maps of a 3-manifold into a hyperkähler manifold. So in our case, what we want to do is start with a flat hyperkähler manifold, just a quaternionic vector space, you might say. Though kind of the more conventional way to think about this is I take a complex vector space and I take its cotangent bundle. That always has a flat hyperkähler metric. And I assume that my original complex vector space N had a compact group acting on it. And I can construct what's called the gauged sigma model. So this is basically looking at maps of the 3-manifold rather than into just this vector space, but into its stack quotient. So gauging is the physicist way of talking about stacks. And when we do this, we get a n equals 4 supersymmetric 3D quantum field theory. And there's a lot of interesting things to say about those, but the important thing for us is that kind of theory, because of the supersymmetry it has two topological twists. So there are two ways of making a TQFT from it. And each of those topological twists has a moduli space of vacua, which is just, I look at the algebra that's given by the Hilbert space of S2, and I take spec of that. That's commutative because I can take two S2s and move them around each other inside a bigger S2. So it's a commutative ring, and I can look at its spec. And for the kind of dualizable TQFTs that people in math have usually heard about, well, it's going to be a finite dimensional algebra. Its spec is going to be very small. But the theories that come out of this n equals 4 story tend to have very large moduli spaces of vacua. So when I look at the B twist, I get what's called the Higgs branch. And this is something that mathematicians have been studying for a very long time. In particular, there's this paper of Hitchen, Karlhede, Lindström, and Rocek, which was basically looking at this as a way of constructing hyperkähler metrics by hyperkähler quotient. But if you sort of go through their paper, they motivate everything in terms of this gauged sigma model. So that's actually sort of the best reference I found for mathematicians to actually kind of get a sense of what the hell is going on in this sigma model.
Rocek actually played an important role for this and also for the work of Marco.
So sorry, I couldn't actually make out what you said there.
I said something about Rocek's contribution to a work of Marco. What work?
So it's a talk that Ben held a few weeks ago when Marco came to visit.
Marco Gualtieri gave a talk a couple weeks ago that also involved Rochek's work, Amihai says.
That is true. Yeah. Yeah, I mean, I don't know. Maybe this isn't the right one to emphasize. I don't know. This is sort of the paper the best paper I found that sort of describes this stuff. But obviously all of this stuff developed over a long period through work of many authors.
She said that normally when you take spec, you don't get something very big, but in these cases you do. Is that what you said?
Well, so what I was saying is if you're used to kind of the usual mathematical story of TQFT, they'll be thinking about a dualizable theory. And so the Hilbert space assigned to S2 is necessarily finite dimensional. That's a necessary theory to be dualizable. So often people who are talking about TQFTs will assume that's the case. And so you're taking spec of a finite dimensional algebra, and so you get a finite set of points.
I see.
But in this case, that isn't what happens. The theory is very much not dualizable. And get a big infinite dimensional algebra, right? You get things like the functions on a symplectic singularity. Right? I don't think I said these words because it's not kind of that important for what I'm going to talk about later. But these Higgs branch and Coulomb branches in this 3D n equals 4 case, typically turn out to be symplectic singularities.
Right.
And they automatically get a Poisson structure that comes out of the physics. I mean, one way to say this is like they're really kind of they're the cohomology of an E3 algebra, and the cohomology of a 3 algebra always automatically has a Poisson structure. And just in many cases, that Poisson structure turns out to turn the spec into a symplectic singularity.
Right, okay.
Yeah, and so in the Higgs branch is, a hyperkähler quotient. You can sort of explicitly write down, I look at T star of n, I look at the complex and real moment maps, look at some fixed level of those, and I mod out by the action of the compact group. So it's sort of an explicit quotient construction. It's something mathematicians understand pretty well, and have been thinking about for a long time. On the other hand, the moduli vacua for the A twist. So there are these two twists, which somehow from the perspective of the physics are kind of on an equal footing. But somehow the B twist leads you to this very concrete thing that we understand very well. And with the A twist, one gets something much more mysterious. So that's what I want to talk about today, because that's kind of been the main thing I've been focusing on for the last few years. So this moduli space of vacua for the A twist, well, it's birational to the cotangent bundle of the Langland's dual of the torus of your group mod the action of the Weil group. So what physicists would say is classically, this is the answer you would get for what the Coulomb branch is. Somehow this T star of T check is reflecting certain kind of fields in your theory. And so you get this, pretty concrete space. But then they say, oh, but that's not right. That's not quite the right thing. You have to do some modifications to this, which, I had usually heard described as in like, oh, there's some change to the hyperkähler metric. And so you have to kind of change the topology of the singularity to go along with this change in the hyperkähler metric. But it wasn't so kind of clear what was happening. And then a series of work in the 2010s, so by Amihai with Cremonese and Zaffaroni, Bolomoro, Dimofte, and Gato, and Braverman, Finkelberg, Nakajima, sort of gradually brought this picture into view. So, I'm not going to sort of write down the definition of the Coulomb branch in terms of the Affine-Grossmannian. That was kind of the way that BFN phrased it. I'm going to give you at least in some cases, another description for it. So the important things to know about it are, well, it's birational to this quotient. So that means I can think of its coordinate ring as a subalgebra of the fraction field of this cotangent bundle. Take the Weyl invariance, right? So this guy, I should be using my pointer now. This guy is the function field of T star of T check mod W. So if you're birational to that, that means your coordinate ring is a subring of this fraction field. And the rough idea is, oh, sorry, I somehow messed up the notation here. If I think about this cotangent bundle, so that's the Lie algebra of the original torus times the Langland's dual torus on that. So the functions I get are polynomials in T dual and co-characters of my original torus are functions on T check. And this M lambda here, I was trying to use that to denote the function given by a co-character thought of as a function on the Langland's dual torus. So it's sort of useful to think about, I fix one of my co-characters, I have a copy of sim of T dual, which is all the functions on the cotangent fiber. And then what happens when I act with the Weyl group? Well, the Weyl group acts on my set of co-characters, and then it sort of acts in a corresponding way on sim of T dual. And so you can get an element of the invariance that sort of sits over this orbit of co-characters by fixing on one of the co-characters, the coefficient, which has to be an element of the invariance of the stabilizer. So this is the kind of picture to think about. And the way you get this, the sort of vague picture you should have for this Coulomb branch is I take this M lambda and I add in some rational functions. I multiply it by some additional polynomials that come from weights of n. And I also divide by some polynomials coming from the roots of G. So somehow having more roots in G kind of makes you divide by more stuff. Having more weights in N makes you multiply by more stuff. All right, are there any questions? This is just kind of give you a picture of, what kind of world we're in, where, you sort of have these co-characters. These are usually called monopole operators. You multiply them by these elements of sim T dual. Those are called dressed monopole operators. And you can think of them as elements of the fraction field, but they're not just sort of this co-character, just a symmetrized thing. There's sort of some extra factors that come up, which are exactly kind of the information of how is this Coulomb branch different from T star of T check mod double. All right. So one nice way to think about this is inside T of W. So let's see, I thought I had mentioned this somewhere. Okay, well, let me just mention.
Maybe I just say your heuristic description seems to make it clear that if you use n equal to the adjoint representation, then you just get the thing you wrote down, the ordinary.
Yes, that is true. If n is the adjoint representation, then exactly those numerators and denominators cancel, and you just get T star of T check.
Yeah.
So I somehow should have said this, and I managed to not write it down. If I take T star of T check mod W, well, there's a projection, right? Since T check is a Lie group, its cotangent bundle is trivial. And so I can project down to the cotangent fiber. And since I mod it out by W, I mod out but to the cotangent fiber mod W. And every Coulomb branch has a map that's sort of modeled on this one, that's sort of matches up with this one under this birational morphism, which I'm calling pi. And if I look inside T, there's an open subset where no roots of G and no weights of N are 0. And over that subset, this sort of classical prescription is correct. So if I restrict to the subset, I take the pre-image, oops, doing the wrong thing here, pre-image of this open set. So I'm sort of removing some divisors from my Coulomb branch. Then I just get, take T check, multiply it, well, now by this open subset of the torus, and mod out by W. So one kind of useful way to think about Coulomb branches is they're gotten by sort of taking this open set and then doing something a little bit interesting on these hyperplanes where things go wrong. So one way to say this, I'm not going to try to state the theorem precisely, but BFN have a theorem which basically says, well, you can really completely reconstruct the Coulomb branch by just what's happening generically on these hyperplanes. And this is sort of another one of these manifestations of Hartog's theorem, right?
Is this a consequence of the statement that it's a normal affine variety?
Yes, I mean that's sort of the important thing. It's a normal affine variety, so indeed, kind of all the information is in codimension 1 primes. It's the intersection of all of the local rings for codimension 1 primes. And of course, there are a bunch of codimension 1 primes that come from this open subset, but those are boring. Those are the same as the cotangent bundle of T check mod W. And so the only interesting codimension 1 primes are take one of these hyperplanes and take its pre-image. All right. So we sort of have to say what's happening there. But before we kind of go that direction, I want to talk about something which has shown up less in previous talks I've given about this stuff. So the first few slides, those would have been, I could have given talks for the last 10 years that started with those 3 slides. But there's a structure that I am still a little sort of don't know the best way to think about. So in part, I'm giving this talk in hopes that some of you will understand it better. Let's talk about the case where I just have a torus and I have the 0 representation. So in that case, well, that turns out to be the same as the adjoint representation for torus, because the adjoint representation is trivial. So I just get the cotangent bundle of the dual torus. And if you look at that for a moment, you realize, oh, actually, that's a group scheme, right? It's not just a random algebraic variety or even a random symplectic one. It has this map down to T, and every fiber of that map has a group structure because it's T check. And this particular group scheme, has a strong connection to Hamiltonian T actions, right? Somehow, if you have a Hamiltonian T action, maybe you should really think secretly it's not, Hamiltonian T check action. Maybe you shouldn't really think it's just T check that's acting. Maybe you should think it's this group scheme acting, because of course you now have a guy that fibers over T check. I mean, this is sort of a little bit silly, but somehow it plays a little bit better with the symplectic story to think about having a symplectic thing. Maybe more surprising, well, this is kind of, pouring old wine into new bottles in the case of a torus. For a non-abelian group, one still has the same property. You still get a group scheme. And this group scheme structure comes from push forward of the functions on the Coulomb branch you can think of as the Borel-Moore homology of the affine Grassmannian. And this group scheme structure comes from the diagonal copy of the affine Grassmannian inside 2 copies. So it's always the case that if I take this pure Coulomb branch, that's an abelian group scheme, which is flat over this base TW. So this is the same map I was calling pi before. The fibers of that map, every fiber is a group. And the groups all play together in a nice way, which group scheme is the nice way of saying that.
Sorry, this X was the T mod G, or what was the X?
Oh, sorry. This is no. This point I was making here is if I have X, a Hamiltonian G space, sorry, a Hamiltonian T check space, then I get this kind of natural correspondence where I can just take the fiber product. I mean, this is, I'm being a little bit silly here, right? This is T check times X. So I have an action map going to X, and I have an inclusion map going into this product. And the Hamiltonianness of the T action is exactly the fact that this guy's Lagrangian.
I see. Okay, and now you said that extends to all G.
Yeah, well, for all G, there's a group scheme that plays a kind of similar role. And, somehow like, right, it's a little bit weird to think about, I'm going to want to use later that I have like a Hamiltonian action of this group scheme, but what exactly does that mean, right? Because now I don't have the same group in every fiber. I'm going to get different groups in different fibers. Let me actually get to that next. So actually for any reductive G, I should probably just say simple G to make my life a little easier. This guy has a nice description. So the way you should think about it is you have the Sloterdijk slice to a regular nilpotent. And that's actually naturally identified with T mod W for reasons having to do with, wanting to be mapping into G dual. I'm taking the Langland's dual group of G. And what I want to look at, what describes this MG for me, is I look at this, the elements of the Sloterdijk slice, and I look at their stabilizers under the coadjoint action. So this is a sort of universal centralizer. Or I should say, just say regular centralizers. Let's see. Is the special word, regular centralizers. For GLN, this is something really concrete. We have Cn mod Sn. So I'm looking at unordered n tuples. To every unordered n tuple, of course, I have a polynomial, which is the degree n monic polynomial, with that n tuple as the roots. And attached to that polynomial, I have a companion matrix. So this is, the sort of natural way of cooking up a matrix with minimal polynomial equal to that, to this P. So my constant section in the GLN case is just, I have an element of Cn mod Sn. I map it to the companion matrix of the polynomial with roots given by my unordered set. And so what I end up looking at is the centralizer of that matrix. So right, I'm fibering over Cn mod Sn, and the fiber over a point is take a regular matrix where the eigenvalues are given by the coordinates of my point and look at the centralizer of that. And this companion matrix is just kind of a systematic way to make a regular matrix, one with maximal rank with fixed eigenvalues. All right. So if all the roots T are distinct, that guy's diagonalizable. And its centralizer is just the diagonal matrices in the basis where it diagonalizes. So I just get a torus generically, but then over points where some of the eigenvalues collide, suddenly I don't get a torus anymore. I get sort of some funny combination of torus and unipotent. And if I set all my guys equal, what I'm looking at is I'm looking at a single Jordan block. And I'm looking at the centralizer of that, which is actually unipotent. Well, sorry, it's unipotent times scalars. So it would be unipotent if I looked in SLN. All right. Are there any questions? This is a really important idea I'm going to use later. So this is a very interesting group scheme, and it happens to be a nice description of this Coulomb branch for GLN, the pure GLN. So one of the things I would really like to understand better is like, if you're looking in the physics picture, like where does this group structure come from? Like, is this something you expected to see? Is it a surprise? I don't know.
Yeah.
So for GLN,
Right,
for GLN, the centralized was just the powers of the regular element, right?
Well, I mean the Lie algebra is spanned by those.
Yeah.
Understand what you mean by the powers of that, like what
Yes,
does
I was thinking of the Lie algebra. So you got some, you got some determinant on that space that maybe not so obvious for it to
I
be.
mean, one way to say this is it's the polynomials in the companion matrix,
Yeah.
which are invertible, which is
Yeah.
exactly, you have to apply a polynomial, none of whose roots agree with one of the TIs to the companion matrix. So you'll also see this description of this guy in terms of pairs of polynomials, one of them monic of a given degree, one of them of strictly lower degree, such that none of the roots overlap. And it's exactly the monic polynomial is giving you the TIs, and then the other polynomial is what polynomial do you apply to the companion matrix to get your guy. Another way to say this is it's the unit group of polynomials mod and U mod PU. Right? So if U has distinct roots, then that's just a product of C stars corresponding to the different roots. Whereas if some of the roots start colliding, then you get unipotent elements in that unit group.
Right. So I mean, you don't actually have to take the Sloterdijk slice. You could take this slice where you just look at the rightmost column, right? And this is still a transverse.
Yeah. I mean, yes, a slice. It doesn't have to be the one that's Sloterdijk actually defined.
And then it's just a bit more obvious that the TI are the coordinate functions on the if you do that.
No, I agree. I don't know. I feel like we've all agreed that's what Sloterdijk slice should have meant. So
Yeah.
we just kind of say Sloterdijk slice when we actually mean that one.
Yeah. Okay.
All right. So I'm only going to consider the case where G is a product of GLNs. And so that's the only pure case we'll worry about, that I have a product of GLNs and I'm getting this sort of centralizer construction. So how do we incorporate this representation? So this is kind of an interesting story, which I think, it's taken us a while to appreciate. So for every weight, I have a map from the torus to C, and I have a map from C star into this dual torus. So if I have a weight, I can think of it both of these ways. I can think of it as a linear function on T, or I can think of it as a co-character into T check. And I'm going to do a strange thing, which is I'm going to compose these guys. So I'm going to start at T, I'm going to map to C, and then I'm going to take the rational map from C to C star. So I'm going to have a problem if at 0, but I already sort of know that places where my weights vanish are kind of bad. And so I get a rational map from T to the Lie algebra T to the torus T check. All right, so this is a strange operation, and it's not defined everywhere on T. It's going to blow up at, or it's going to not be defined at places where one of the weights is 0. But I can take these rational maps, and then using the group structure in T-check, I can take their product. So I end up with this kind of strange rational map where T maps to a big product in T-check of these guys I've gotten by taking my weight and sort of composing the function coming from my weight in 2 different ways. So over the place where none of my weights vanish, this defines an automorphism of my space, right? I get a perfectly good element of T-check at every point as long as none of my weights vanish. And I can use that to kind of, take this fibration and do a kind of gauge transformation on it. I can rotate each of the fibers, but I'm rotating different fibers by different amounts. And when I go to one of the places where my weight vanishes, like the amount that I twist my fiber by blows up. All right.
Sorry, so what is the automorphism over that open locus in terms of this?
So this product, I'm taking this product, this is the product in T-check.
Right.
Right. So this is, I take an element of my Lie algebra, I apply the weight to it, I get a complex number.
Right.
Then I also think of the weight as a co-character into T-check, and I apply that co-character to it to get an element of T-check. But that only makes sense if the number I got from my Lie algebra was not 0.
Okay. But that defines a map from T circle, little t circle to big T check.
Yeah.
And then what's the automorphism then?
So the automorphism is in this product over each point in T circle, I multiply by that element of T-check.
Okay.
So it really is a gauge transformation.
Okay.
All right, so sort of, what I'm ultimately going to do is I'm going to be sort of saying I want to take 2 copies of this guy and identify them using this automorphism. And then when I go to one of these boundary divisors, that identification isn't going to work. Okay, so I'm going to have to make a weird assumption on my representation that I don't have any pair of weights such that I get one from the other by multiplying it by a negative rational number. So lots of representations satisfy this property. Lots of representations do not satisfy this property. I'm ultimately going to be interested in quivers. If you want this property for a quiver, you shouldn't have any loops because that will completely mess you up. And you shouldn't have 2 opposite parallel edges. So you shouldn't have 2 nodes and edges going the opposite way. But the Coulomb branch only depends on the quiver without orientation. So I can always orient my parallel edges the same direction. So I'm only going to get in trouble in quiver land if I have loops. And someday we'll fix that, but not in this talk. Okay. So under this hypothesis, I can write the coordinate ring of MGN as a subalgebra of, well, I could have said the fraction field, but I'm going to do something a little smaller in the function ring of MG0 restrict to this locus over T circ. So I've pulled out all of these bad divisors. And this intersection is I'm going to look at 2 copies of the function ring of M of G0. So one copy is, this is a open subspace inside M of G0. I can restrict functions on M of G0. That's the obvious inclusion. And then the other copy is I twist that inclusion by this automorphism. So I can restrict, and then on this guy, I have an automorphism that comes from multiplying by this section epsilon I wrote. You can say this in sort of a slightly more geometric way. This is a statement about algebras. you can turn that into a statement about affine schemes. So I have a copy of MG, I have a copy of MG. I can map in this open subset in two different ways. The obvious way and the way twisted by this automorphism. And the Coulomb branch is the push out of this diagram. It's the unique affine scheme that has maps from both of these copies of MG that makes the whole diagram commute. All right, everybody with me? So a version of this theorem was proven in Telemann's paper on the role of the Coulomb branch in 2D gauge theory, I think he called it, under some slightly different hypotheses. So I'm putting mine and Tom's name on this because we proved that you can do this under these more general hypotheses. All right, so what does this look like in an example? So if I have C star acting on Cn by weight 1, then this guy was calling epsilon. So first note, there are no weights which are multiples of each other under negative rational numbers. So that's good. I satisfy my hypotheses. And this guy epsilon is just the map, take t to the n. I'm thinking of that as a rational map from C to C star. So the two inclusions I was talking about, well, one of those, I'm making little t my coordinate on the torus and little s my coordinate on t check. These are C and C star. So t is a polynomial coordinate, s is a Laurent polynomial coordinate. So these maps from here, the usual inclusion is I send t and s to t and s. Here I'm thinking of t as a coordinate on C star, and now I just think of it as a coordinate on C. The twisted inclusion is I map t to s t to the n. And that's okay on this subspace because here I'm assuming that t is not 0, right? But that wouldn't make sense if I was trying to map from here to here because t could be 0 and then this guy, well, yeah, it's actually mapping back the other way that gives you trouble. The point is it's not an automorphism if t is 0. And if you go through this intersection description for doing this push out, then what you'll find is that you get spec of S inverse. So that's okay. But I have to get t to the n times s. So I need to have a function that's a pullback of a regular function on here and a regular function on here. Of course, s t to the n is a regular function on here and a regular function on here. But if I took s on here and tried to write it as its pullback would be s t to the minus n, and that's not a pullback of a regular function on here. So I get S inverse t to the n s, and you can work out that actually spec of that is C2 mod Z mod NC. You identify S inverse with U to the n and t to the n s with v to the n, where u and v are coordinates on C2, and then t gets identified with uv. All right. So this is just sort of an illustration of how this works. Before I had, Laurent polynomials in S tensored all polynomials in T, and this kind of gluing construction showed me that basically I'm getting, so if you think about the picture inside Laurent polynomials, so if this is my exponent in T, and this is my exponent in S, right? The Laurent polynomials in S and usual polynomials in T is like this half space. And then the pullback from here, it's kind of tilted. Hopefully I'm going to get this tilt the right way. Sort of these guys. And so the monomials I get are the ones that are in the intersection. So it's okay to have negative powers of S, but if I have a positive power of S, it has to bring a positive power of T with it, which is how I get this algebra. All right, so why did I want to tell you this theorem? I mean, in part, I think it's a nice theorem. It sort of tells you a little bit about how to think about the geometry of these Coulomb branches. But it's also very useful for proving things about Coulomb branches, because you can prove things kind of before gluing, and as long as they're consistent with the gluing, then they kind of automatically carry over. So for example, I have this group scheme MG. It obviously acts on itself. And then if I think about this push-out diagram, MG acts here, MG acts here, MG, I mean, I've got to be a little bit careful about the base, but it acts here as well. And everything's compatible, right? I'm multiplying by a section of this group scheme, and it's an abelian group scheme. I'm multiplying by a section commutes with the action. So under this push-out diagram, this glues to give me an action of MG on here. And again, this is something that I think it would be really good for us to understand better physically what this means. I have this action of MG on MGN. And one way to think about this is, well, MGN is birational to MG. And so that uniquely fixes this action, right? It tells me that on a generic fiber of MG over its integrable system, that's just a copy of T dual, and it acts on T dual in the obvious way. And the kind of magic is, oh, by this gluing, it just automatically extends.
Can he give an example of
I'm sorry, I couldn't understand that.
U1 with n flavors versus U1?
I would like an example of U1 with n flavors versus U1.
Yeah, because
Can you do that one?
U1 with n flavors versus U1?
I think it's similar to the example you had before.
So, I mean, if you mean for this group scheme action, right?
Yes.
For G equals a torus,
Yes.
well, MGN is, right, T times T check. And so this action, it's just the fact that the Coulomb branch is a hypertoric variety with an action of T dual, right? T dual is the flavor symmetry acting on the hypertoric variety if you think about it as a Higgs branch. And so this is just the fact that I get this Hamiltonian T check action on the Coulomb branch for, MTN.
I see. Okay.
Yeah, so I mean, the interesting part is the non-abelian guys.
And you say there is a natural extension to the non-abelian case.
Right, in the non-abelian case, I mean, the same thing happens. And, if you think about it in terms of these fibers of the integrable system, everything's kind of determined by the birationality, right? You're still birational to, the cotangent bundle of T check mod W. And so, for a generic Coulomb branch, the fiber is still this torus. And so ultimately, this is coming from the fact that this fiber is still a torus. But it's much harder to see, like, well, why is everything compatible with kind of how things blow up and degenerate at these hyperplanes.
Again, you're intersecting two copies of M of G, you see? And why is it again obvious that M of G acts on the intersection then?
if you're thinking about the scheme picture, it's not an intersection, it's a push out. It's a
Oh, right,
union over some subset, right? So
Right.
somehow morally, you should think about this as like, I take two schemes, identify an open subset of them. Well, if I have a group scheme on a group action on the two schemes, which is compatible with the open subsets and the isomorphism commutes with the group action, then of course the group, acts on the guy where I stick them together.
Oh, I see. So your point is that this M of G action on there's two different copies of M of G restricts to the same action over this open.
Yeah. I mean, one way to say this is right, like, so, there's that thing I just physically described, which is the coproduct in the category of schemes, right? And that coproduct in the category of schemes, kind of obviously gets this action. And then MGN is the affinization of that coproduct, right? Or not coproduct, sorry, push out. Right, it's coproduct over a morphism. So like what I'm doing is, sort of somehow it's geometrically obvious that it works for the push out in the category of schemes. And then push out in affine schemes is do push out in schemes and then affinize. So right there is a kind of horrible Frankenstein scheme where I just take two copies of MG and glue them over this open set. And that obviously has the MG action, but it's extremely not affine. So when I affinize, well, because affinization is a functor, the MG action comes along for the ride, but I actually change the geometry of the space quite a bit.
Yeah, it's a little bit confusing thinking about why MG is acting on this union. But I guess it's acting on one. If you think of M of G as one of the two things, then you have this isomorphism commit to the other one. Now you take some kind of diagonal action for this isomorphism.
I mean, for this union, it really is, right? Like I have a group scheme acting on, if I have two spaces that a group scheme acts on, and I identify open subsets of them in a way that's compatible with the group scheme action,
Right.
obviously group scheme acts on the coproduct.
Right. Yeah, I guess because you have this automorphism in there, it doesn't seem obvious that it's compatible with the group scheme action.
I mean, the fact that it commutes without automorphism is just that the group is abelian.
Okay.
Right? The automorphism is multiplying by a section of the group scheme.
Okay.
And the group scheme is abelian, so that's commutes with the group scheme action.
I see. Okay. All right.
Yeah, I mean the weird thing is that the group scheme is abelian. Like somehow that's the part that really messes with your head.
Okay.
Okay, great. So we can extend this a bit. We're with 7 minutes left. Am I actually supposed to stop at 10?
No, we started late. If you're not busy, we can continue.
Okay,
We
great.
have some time.
Well, let me know when I should stop. I won't be, people can always just run away. I won't even notice. All right. So if I have a reductive subgroup H of G, then there's a generalization of this, which is I can take MH and MG acts on that. And I should be a little bit careful here because, of course, MH and MG aren't over the same base. So I should actually take MG and I should base change to the Lie algebra of the torus of H mod its file group. All right. So just as I had a slightly funny hypothesis on my statement about producing this Coulomb branch via gluing, I hope someday to fix this, but I'm not ready to fix it yet. I need a similar kind of hypothesis on my gluing, which is, I say an inclusion is gluable if for every pair of weights of my representation, well, either when I restrict them to H, they're not multiples of each other, or they are, before I restrict, they're multiples of each other by a non-negative rational number. So before I had to worry about things which were negative multiples of each other, but now I have this slightly funny thing where I don't want things where these guys are multiples of each other, and it's not, it's just important here that this is after restriction to H, this is not after restriction to H. And this is just, it's exactly the hypothesis I need to make sure that this push out picture still works after base change to C of H. All right, so if that holds, then I get a new description of MGH, which I can get by, I take the Coulomb branch, sorry, this is MHN. I take MGN, so I'm trying to describe the Coulomb branch for this subgroup by starting with the Coulomb branch for the bigger group. And the sort of idea here is, well, I have to change the group. How do I change the group? Well, I sort of know how to change the group in the pure case. MH has an action of MG on it. You can even think of it as a homomorphism of group schemes. So what I do is I take the product of these guys, and this product is over the base of the Coulomb branch for G, and I mod out by the diagonal action of MG. So I mean, the way you should think about this is essentially a Hamiltonian reduction. This is basically a moment map condition, and then I'm modding out by this group.
Reduction with respect to the complexes.
I couldn't hear what that was.
This is a Hamiltonian reduction, Amihai, is that
I mean, in the sense that if I do this fiber product, I get coisotropic submanifold of the product. And modding out by this group is modding out by the null foliation. So that's one way to think about Hamiltonian reduction. So, I mean, it's not Hamiltonian reduction just, in the sense that you would learn in your first symplectic geometry class, because it has this weird property that over different moment map values, I have different groups.
Typically, after the division of the group with a group action, here he's putting a modulus space.
Yeah, well, this M of G, I guess you're thinking of it as like a group, but it's a group scheme over this C.
Yeah.
So for each fiber, you have this group there.
I mean, you should think of the kind of thing you should think about is if you have T star of G, right? I mean, I made this point about the torus, but it's not actually different for the group, for a non-abelian group, right? This is G dual times G. So if I have a Hamiltonian group action, I could think about this group scheme as acting here. And then somehow it's some natural kind of step up to be like, well, why do I have to put the same group over every fiber, right? I could have a group scheme which is itself symplectic and maps down to a nice base with Lagrangian fibers. I mean, that's what's happening here, right? I have a group scheme and it maps down, the whole thing is symplectic, and it maps down to a base with Lagrangian fibers. Well, this is just some generalization of that idea.
I see. So M of G is not T star of G, it's some generalization.
Yeah, I mean, you should think of it as like T star of G, but the fibers change.
I see.
Now, what's the condition here? I mean, are you assuming that H contains a maximal torus or something? What is the condition here couldn't you have that this M of H is much smaller than the M of G, and why does the G
Yes.
act on the
Yes.
H?
Right. I mean, the way you should think about this is that MGN is the same size as MG. So those sizes kind of cancel.
Right, but why does the MG have to act on the M of H? Obviously, like you could have a H star across H, and you have this G star across G, and it's like you're saying that the G is acting on the H or something.
Well, I mean, I have to somehow incorporate the information of how H is a subgroup of G.
Yeah, but normally H acts on G then by multiplication, not the other way around.
Right, but there's a dual here, right? There's a T check.
Yeah, but nonetheless, we don't know anything about how big the torus of H is, right?
That's true. But, so for example, if G and H are tori, right, then I have H sitting in G. And if I take the dual torus, then the dual torus H is the quotient of the dual torus of G. Right? So that's like the first example to think about.
Okay. So you're saying that even if H and G are not tori, when you take their yes.
Yeah, I mean, it's still true that if I take a maximal torus of H, there's a maximal torus of G that contains it.
Right.
Right. And I have a map the other direction on the Langlands duals of those maximal tori.
Right, right. Then you have the Weil group involved here, I guess. But
yeah.
now you're saying that even with the Weil group, then you're going to get an action to it.
Yeah, I mean the map between bases is relatively easy because I can describe this base CG as the Lie algebra of G mod G. Right. So I obviously get a map there from C of H mod H.
That's
and
right.
That's sort of the only compatibility with the Weil group I need. Right. If I take a fiber over a generic point here.
So for the fibers, you're normally going to be just having this torus action you were saying before, but you could have some special fibers where it's more complicated.
Yeah, where something sort of degenerates, blows up.
But now you're saying it's always going to act. It doesn't seem completely obvious. Okay, you're saying that the M of G has to act fiber-wise on the MH.
Yeah, yeah. Right. Okay. I mean, this is it's really sort of a base changed version of MG. I'm kind of hiding that in there. Right. The thing this guy naturally maps to is C of H. And I'm worried that I actually should have put H there, but we'll worry about that later.
But I mean the MGN maps.
Oh no, it is right. Okay, good. Yeah.
I think it's correct. I just didn't know that this MG acted on the MH. That's all.
Yeah, I mean, it just comes from the fact that I have a map. So I have an inclusion of the affine Grassmannian of H into the affine Grassmannian of G. And the map on functions dual to the action map is push forward from the graph of that map into the product GUR of H times GUR of G.
Okay.
Right. So it ultimately comes from the fact that there's an inclusion of GUR of H into GUR of G.
Okay. Okay.
All right. So, I mean, I guess the question is, do people, should I stop or should I keep going a bit?
First line, the right hand side, there should be algebra. Like, I think you define just good. It looks like you write the left-hand side or right-hand side twice, and then you take the geometric ones. Ah, I think it's a true. Yes. I guess there's an extra m of g that's pointed out on the top equation, right-hand side.
Oh yes, there is. You're right.
So can we go longer? Are we okay with going longer? Is it 3:05? It's 3:05 now. Do you need to go somewhere? Should we continue for another 15 minutes? Yeah. Let's try to go for another 15 minutes.
Okay, right. Okay, so what situations do I want to apply this in? This is sort of, it's a nice general theorem, but what are you gonna? There was a reason that Tom and I were doing this. There was a specific problem we wanted to solve. So we have this slightly annoying glueability hypothesis, but it's not that bad in practice. So this kind of situation where we mainly want to apply this is if I take a quiver, then I can do what we call a dismemberment, which just means I take, at each node of the quiver, I have the option to kind of slice through the node. I kind of picture this like when you cut through a chicken leg and sort of pull off some of the edges, or kind of pull apart portions of the graph. If you want to say this in sort of a nice way, you have a map of graphs that's a bijection on the edges. So it might be that it's not injective on the nodes. You might have multiple nodes going to the same guy so I have this Q check. I might have multiple nodes in Q check going to the same node in Q. And I think of that as like I have kind of these pieces of my graph and I stick them together. All right. So when you do this, you get an inclusion of the product of GLNs associated to nodes of Q into the product of GLNs associated to the nodes in Q check, right? It's just for all the nodes going to one node in Q, I do the diagonal inclusion. All right. So when I take the usual representation to a quiver, right? So I take the edges in my quiver, I look at from the vector space on the tail to the vector space on the head. I take that representation. So because the edges stay the same, this vector space won't change when I do a dismemberment. The only thing that changes is what's the group that's active. And so when I do this dismemberment, I get a bigger product of GLNs acting on the same vector space. So I get one of these situations where I have a reductive group, the product of GLNs for Q check, and inside there I have a subgroup, the product of GLNs for Q. And it's often easier to figure out what the Coulomb branch for this sort of more dismembered quiver is, and then try to stick it together by getting rid of some of this, the gauge group. So this is going to satisfy the hypotheses of our theorem if the graph has no edge loops. And anytime I have a node and two edges going between a pair of nodes, I keep those together. So you could imagine a situation where I had two nodes, two edges. I cut that apart into two edges going between separate nodes. That's a perfectly fine dismemberment, but it's not going to satisfy the hypotheses right there. And I should probably mention here, I don't really think these hypotheses are necessary, but we haven't quite figured out how to get rid of it. Okay. And, particularly the no edge loops thing is annoying because edge loops are important, but, lots of interesting graphs are covered.
So every pair condition is saying that it sounds like it's saying you want all of the edges between two vertices to go to the same two vertices in the cover. No?
Yes, that's exactly what I want. Because what I want to avoid is I don't want to have two different weights for the bigger group going to the same weight when I restrict.
But then it sounds like you're not dismembering too much then if you're
I am. It's just not guys that, I mean, this that restriction doesn't tell you anything if your graph doesn't have multiple edges between a pair of nodes. So if your graph is simply laced, then it's no restriction at all.
That's true, yeah. But somehow, okay. You're
So
you're
I mean, in
adding more
particular,
verse.
like you could completely reduce to the case of graphs with two nodes.
Mhm.
This is actually something that I would like to understand better. Like what do you get when you only have two nodes? And do you learn anything interesting from the fact that for all quiver gauge theories, the Coulomb branch is kind of put together from these guys with two nodes?
Okay.
The example that sort of seems more relevant is if we have this situation of I have some complicated graph here. I have a node, it has label n, and I either have and want to consider removing or don't have and want to consider adding a leg where the dimension vector drops like this. So we end up with a really nice description of what adding this leg does. So if Q is this guy without the leg and Q prime is the guy with the leg, so Q would actually be the dismemberment in this case. I take the Coulomb branch for MQ. I just take its product with GLN. So this is really a fiber product with something a little bigger, but the fiber drops out. And you're just taking the product with GLN. And then you divide by the action of M of GLN. And I'll note here, this guy still has a map to Cn that comes from the fact that the GLN was already part of the gauge group there. So I'm using this map to be my base for the MGLN. One particularly nice thing here is, so MGLN, right? Every fiber of that I can think of as a subgroup of GLN. It's the centralizer of an element of GLN. So it acts on GLN on the left, by left multiplication. And so one thing you can see immediately geometrically here is this guy has a GLN action by multiplication on the right. And this is the one that Ami always likes to use. So, right, all of these nodes are balanced here. And so one gets a GLN action on the right. All right.
Balance translates to this.
Sorry?
Amihai says the balance translates to this. At least
Yeah, well, I mean, the balance translates to like, right, having operators that are in the right degree to give you the Lie algebra of this GLN.
Okay, so when you say, for example, you don't mean it as an example of what you had before, but you're going to apply the dismemberment to this Q prime in order to deduce the theorem. Is that the point?
Yeah, I mean, I was maybe not as good with the notation here. I mean, this is an example of the theorem from before, where I'm thinking of Q as a dismemberment, Q and this node floating off in space as a dismemberment of this guy. So, I mean, what's happening here is if I look at just this guy, n up through 1, then I get Cn times GLN. Where I'm thinking, this Cn I'm thinking of as the constant slice. And so I'm taking the fiber product over Cn with Cn times GLN. Well, let's just take product with GLN.
I see. Okay.
All right. More generally, there's sort of a more general situation where this leg has a more quickly decreasing dimension vector that comes from a partition. And then instead of just taking this full thing, this guy still has a moment map to GLN dual. And you can take the pre-image of a slow to be slice under that map.
Mhm.
All right, so this is maybe sort of the nicest example of something really clean that comes out of this picture.
Max,
It's a question.
yeah, so instead of like a lag of n goes down to 1, so if it's just like a random lag, so can you still make this kind of identification? Like for example, here instead of n and minus 1, we just take n, 2, and 1. So can we still make this?
Well, I mean, that's not a random leg. That's one of these ones that's going to be the preimage of a Sloterdijk slice.
Mm.
Right. So that's the, you just asked about the partition like n-1, comma 1, I think. So I think you're taking the preimage of the subregular.
Yes.
I think I've got that right. Yeah.
Can I ask something, please?
Oh, it's somewhere in between. It's not necessarily.
Sure.
Somebody was saying something.
Yeah, it was me.
Yeah.
So you could do all the class S examples, for example.
Yeah, that was literally the next slide.
Right.
The technically no, because of this thing about like I'm not allowed to have loops. So, for at a physical level of rigor, I'm sure it works with the loops. So like,
Mm-hmm. Okay, that
we
was
at
the
least have a
feedback.
proposal for how to do it for all class S. But yeah, well, so a bit more remains to be checked about that. Oh yes, indeed. If you sort of, I mentioned more Tachikawa here. I should have also mentioned, oh shoot, I'm blanking on the names, but Benini, Tachikawa, and She also. Are really the ones who sort of, at least again, at least that's the paper where I learned about this sort of comet-shaped quiver stuff. So if you want to understand these Higgs branches for Sicilian theories for GLN, you can do duality and write them as the Coulomb branch of quiver gauge theories for exactly these comet-shaped quivers. And you exactly get these type of legs I just said that correspond to Sloterdijk slices. And I just want to mention sort of, if you read this more Tachikawa paper, right, they have this sort of idea of you're going to have a TQFT in the space of, in the category of spaces with kind of boundary components corresponding to G actions. And that when you want to glue two boundary components, you have to reduce by the action of G. So in our picture, the action of this MGLN, and we're talking about GLN here, we could generalize this to other groups, somehow corresponds to having an unpunctured point in the surface. So it's some sort of like kind of local operator story where it's something you can insert at any point, not just at these boundaries. And so when you do reduction for this MGLN, rather than gluing boundary components, you're doing a connect sum. You're making a kind of new boundary component and surgering it up.
So in particular, this is giving a Coulomb branch version of this fusion, right? Where you have two vertices with the same dimension and you glue them together.
Is that called, this is for, is an established operation for quivers?
Like for Hamiltonian reduction, right? If you have two spaces, the GLN action or G action or whatever, and then you want to take their product and take the quotient by the diagonal G or something like this. So it's called fusion, right?
All right. So yeah, I mean, if you want to generalize this for other groups, this is sort of my recipe for doing this, is that if you have a P1 with a single puncture, that's supposed to correspond to taking elements of the regular Slotevy slice, which had appeared before. This is this like constant slice. And look at elements of the group such that when I apply the adjoint action to this guy, I end up in a different Slotevy slice. And the group scheme M of G check is going to act on this. Regular centralizers in G. And so that's going to just act on this by right multiplication on the element G, with taking this X being the map to my base. There's also a description for what you get for an unpunctured surface of genus G, sort of generalizes this quiver having a bunch of loops at a point where you use G check, little g copies of the Lie algebra G check as your representation. And Amihai pointed out to me at some point, I can think of this as doing an abelian Coulomb branch and then modding out by the Weil group, and passing to the abelian guy, I have to insert a -1. So there's also, this is a sort of proposal for kind of all the pieces you need to build up your theory. And again, this MG action, so this sort of transfers over from the abelian case, where it's really just, if I take this abelian Coulomb branch, it has an action of the group T on it. All right, so conjecturally, we can take an arbitrary Riemann surface with the Sicilian theory for G, and have arbitrary nilpotents and combine these all into a description where I, take P tuples of elements of my group that send one fixed guy into the right Slotevy slice. And then I'm going to look at the group that's acting by, I take these regular centralizers, I multiply on the right on these G's, and the product of all of these should be 1. That's sort of accounting for this to MG of the subgroup. All right, and let me just say one last thing. So there's this operation called partial implosion, which turns a G space into a Hamiltonian L space for L Levy. And if you want to understand this operation, you only have to apply it to T star of G. So when you do that, what you get is G mod UP, so the radical of a parabolic with Levy L, T star of that. So that's sort of a big algebraic variety with a bunch of functions on it, but it's not affine. So instead, you take all the functions on it, you take spec of that, you get a copy of T star of G mod UP, but you also get a bunch of other points. So in particular, that affinization is not smooth. All right, so if we do this in the case of GLN, and of course that means L is block matrices for some partition M, then it turns out that this affine closure of T star U mod P is a Coulomb branch for quiver gauge theory, and it's exactly this quiver. I know some of you know this because this quiver is in some of Amihai's papers, where I have a leg going up to n-1, and then I split off into a bunch of legs that correspond to the sizes of the blocks. And it's a new theorem, something we hadn't known before, that these spaces have symplectic singularities and they have finitely generated coordinate rings, because those are general theorems about Coulomb branches. All right, I'll stop there.
Okay, well, let's thank Ben then. Questions?
Yeah, just so I fully understand.
Mm-hmm.
You can construct any quiver using this gluing thing as long as it has, so as long as it's simply laced and has no loops. So star-shaped quivers are kind of just a special case of what you can do.
Yes. And I mean, as I was saying, I mean, first of all, even for guys where you have multiple edges, you still get some statements, but you're just kind of, you can never separate those multiple edges that go between two guys.
Yeah.
The other thing is, I'm really, I think it's extremely likely that these hypotheses are not necessary.
Mhm.
They're just kind of an artifact of how we did the proof, right? So this
I
this
see.
gluing theorem, as I stated, it really needs those hypotheses. But of course, like, there's nothing fundamental about gluing once you've gotten here. So we prove this by sort of basically saying, oh, you know, this guy is glued together from 2 copies of M of H. This guy is glued together from 2 copies of M of G. This theorem is obvious if n is 0. So I can just glue those 2 isomorphisms together to get this isomorphism. But, you know, probably this isomorphism is still true, and you just have to construct it in a slightly different way.
I see. Thank you.
Other questions? So, well, I think that we have a lot to think about. So probably we'll just send you some questions later when we have thought a bit more. We need to digest, I think. So,
Okay.
but thank you so much, Ben. That was really interesting. So thanks.
All right, I do my best.
And yeah, have a great day, and we will digest this and get back to you.
All right, sounds good.
Okay. Bye-bye.